Good afternoon, everyone, and welcome to this fifth talk of the ESA's Climate Change Initiative webinar series. Thanks a lot for joining us. So for those of you who don't know, this webinar series is titled Monitoring Climate Change from Space. It's part of ESA CCI's program Knowledge Exchange Activities. So we launched this monthly webinar series, which is happening every second to last Wednesday of the month at 4 p.m. European time. So if you missed past webinars or you would like to rewatch them, you can have a look at the project website, which is climate.esa.int. It also includes the list of all of our upcoming webinars until October of this year. So the aim of this webinar series is to show how ESA CCI essential climate variables are created and how they can be used to monitor climate change and also drive climate action. So if we go to the next slide, please. For those of you who may not know, the ESA CCI is a major research effort to generate global decade-long satellite data records to track and understand key aspects of the Earth's climate system. So as I mentioned, these data sets are known as essential climate variables or ECVs. And this program, the ESA CCI's program, was established in 2008. And since then, we have now 27 satellite-derived ESA CCI ECVs. And we have also a lot of cross ECVs projects, and all of these data sets are available and open source. You can find them on climate.esa.int/data. And today we will be focusing on a key essential climate variable, which is the land surface temperature. So for this, we are very happy to be joined by Abigail Waring, who's an Earth observation and climate scientist at the National Centre for Earth Observation in the University of Leicester in the UK. She focuses on developing and evaluating global satellite-derived land surface temperature datasets, and she investigates how they can be used to for applications ranging from climate monitoring and environmental services such as heat wave assessment. So in this webinar, she will be talking about how the CCI land surface temperature is retrieved from satellite observations, how it is validated, and why it matters for environmental monitoring and climate research. And she will tell you how to find this data and how to use it in your own research. So we have a chat box that you can use to ask your question, or you can also send them in the chat. And we will address all the questions at the end. And we encourage you, of course, to ask questions throughout the session. Yes, we'll take them at the end. And now, without further ado, I will leave the floor to Abigail. You can now share your screen and start your presentation.
Thank you very much, Amina. I'm Dr. Abigail Waring, and I'm based at the University of Leicester and National Centre for Earth Observation. So I'll be speaking about satellite retrievals for land surface temperature and related applications directly linked to the Land Surface Temperature Climate Change Initiative run by ESA that I directly work on. I'm a climate scientist based in a large surface temperature research group where we have a range of land surface temperature specialists, everything from evapotranspiration, urban and high resolution, climate and algorithm development. And we produce data sets, LST data sets everywhere, everything from the original retrieval and algorithm development all the way up to the finished product, plus many other projects and applications using LST. So I'm going to go through the basics of LST and a little bit about what I do, and then some of the key parts of what our research team have been developing, especially in LST CCI and as it goes forward through the phases. So heat waves are becoming more frequent and more intense and longer lasting. Yet one of the most important aspects of extreme heat, how hot the land surface itself becomes, is less understood than air temperature. So air temperature tells us how hot the atmosphere is. Land surface temperature, or LST, tells us how hot the world beneath our feet is. So during heat waves, this can be really critical. Satellite-derived LST provides a unique view of the thermal landscape of our planet. Here we have two satellite images, LST images during two separate heat waves showing record-breaking surface temperatures. So on the left, we have a heat wave from the CN land surface temperature radiometer, or also known as SLSTR. on August the 22nd in 2022. This was one of the days when Heathrow in London reached 48.1 degrees Celsius at the surface, and at that point had broken that record for the surface temperature. And on the right, we have ESA's recent map of Europe during the UK had hit a new May record threshold. And you can see much of Europe experienced a very strong heat wave. You can see over both pictures a range of temperatures all the way up to and over 45 and 50 degrees. It's very common for land surfaces to be much higher temperatures than air surfaces, and these are based on physical properties of the surface. On the left image, we published this. So my research team, the Surface Temperature Research Group here in Leicester, produced this from SLSTR, and on the right, ESA produced this one from SLSTR. And the blue areas on the right are cloud. So they hadn't classified the cloud in this one or removed it. On the left side, you can see here with the laser pointing. Nope. On the left, you can see there's a bit of missing LST. So that's because thermal infrared cannot be read through clouds. So we will continue on to what is LST. So land surface temperature is defined as the skin surface temperature of the Earth's surface. So if you were to go outside and put your hand on a surface such as concrete or grass, you would be able to feel that temperature. That's what a satellite measures. So it measures how hot the Earth's surface actually is, and this can include soils, vegetations, road, buildings, snow, water, any surface. So this represents the temperature of the surface itself, not to the air above it. So this is not air temperature. And LST is measured by detecting thermal infrared radiation naturally emitted by the Earth's surface. It can also be retrieved in the microwave wavelengths, but we specialize in thermal infrared. But I can talk about microwave later on if anyone has any questions. This then allows temperatures to be mapped consistently across large areas from individual cities to the entire globe. So as Amina mentioned, so LST is currently an essential climate variable deemed by the Global Climate Observing System, and that's along with 54 other variables and is part of the biosphere. So ECVs are critically characterize the Earth's climate system, and improving our understanding of LST means that we can close the gaps in our knowledge, especially since land surface temperature is directly relevant to the Earth's global energy balance. So here, LST is the key driver of global energy balance, linking solar radiation with exchange of heat, moisture, and energy between the land and the atmosphere. Changes in LST modify heat wave fluxes, such as latent and sensible heat exchange in the energy balance and Earth's natural dynamic equilibrium. This drives climate processes, including heat waves, droughts, vegetation stress, evapotranspiration, and the development of urban heat islands. Satellite observations provide global consistent measurements that allow us to monitor change across the entire globe. And high quality LST data improves our understanding in order to predict climate variability and extremes. So improving LST datasets is essential to capturing local scale processes and maximizing the value of Earth observation. And it's also worth noting that the LST, as long as there's no cloud, we can get a LST value retrieval for every pixel across the planet. You can't do this with air temperature. Air temperature are measured by stations near the ground, and you have to interpolate the data in between. So LST, as long as it's clear sky, we get a per pixel value of LST, which is why it's so crucial for climate studies and especially understanding of the Earth's global energy balance. So accurate LST measurements depend on a property called emissivity. And this describes how efficiently a surface emits thermal radiation. So here we can see that air temperature and LST are not the same things, as I said before. So air temperature is typically measured around 1.5 to 2 meters. So you very commonly hear it as T2M at weather stations, whereas LST measures the temperature of the surface that is emitting from the radiation. So surface temperatures can differ substantially from air temperatures. And on a sunny day, surface temperatures such as asphalt or on rooftops and bare soil can be much hotter than surrounding air, while vegetation and water bodies can remain cooler. This makes LST particularly useful for studying heat waves, urban islands, and drought and environmental change. So here you can see that the top yellow line and the bottom blue are day versus night, and the LST versus the air temperature, which the LST is the solid line. So different surfaces such as vegetation, soil, water, and urban materials have different emissivities. So satellite algorithms must account for these differences to convert the measured radiation into an accurate surface temperature. So here you can see at night, the land surface temperatures are often closer to the air temperatures because there is no solar heating at night. And this allows the surface temperature to cool down and cool the air above it. So they are much closer together. And that reduces the large temperature differences commonly seen in the day. As you can see in the daytime, surface temperatures are usually a lot higher than air temperatures, and they're a lot more variable. This is definitely down to, as you can see at the bottom of this image on the right, the type of surface. So every single surface emits heat differently. And this property, as I mentioned before, is known as emissivity. And we have to accurately know this to understand LST. So LST applications, there are a wide range of LST applications, and this is why it is an ECV, because it's extremely critical to climate change. Global and regional climate trends and change. We can also monitor heat waves and extreme heat detections, which I'll talk about a little bit later. We can determine urban heat island assessments, and we can also look at agricultural drought and crop stress monitoring, especially through evapotranspiration studies, and climate change and environmental monitoring. And all of this leads into public health and heat resilience planning. So a key takeaway from this, that there's the whole point of understanding an ECV to characterize the world's climate is to see what is happening, why it's happening, and if we can use this for real world decision making, mitigation and adaptation, whether that's just for the UK or for the whole world. And this really is an important variable in order to understand the whole processes, since the land surface temperature drives energy balance, as we have discussed, but also drives changes in air temperature and is directly linked to weather changes and sea surface temperature. So it's all interlinked as a natural balance. So it's really, really important that we don't just get this data, make it correct, but we actually use it for real world applications. So I'm going to give you a couple of examples. Here are some global anomaly trends that we have produced from one of our merged. We have a merged infrared climate data record. I've also done this for Aqua Modis and produced the uncertainties, and this has been published, so I can always tell you where to find that online. That was one of my first papers of the PhD, and then I applied the same method to here. So here you can take away from this, I have sampled about, I think it's 8 different regions in the world and looked at their trends across time. So here we can have land surface temperature trends for daytime and nighttime from 2000 to 2025, and we can see the trend and the uncertainty in that trend. Now, almost all of them have increased. So regional trends do vary considerably. And this reflects the differences in climate, the land cover, the soil moisture, the urbanization, and the land use change, with some regions that are warming faster than others, and some that exhibit stronger increases in surface temperatures. So here we're not actually looking at the raw LST, we're looking at what we call an anomaly. So an anomaly, if you're unaware, is the analysis that helps separate the long-term climate signal from a normal seasonal vegetation, making it easier to identify emerging trends and such as unusual heat waves. So what we do is we find the average of the LST daily retrievals, and then we remove that average from each day. So the anomaly are the actual change with the seasonal cycle removed. So we can be pretty confident that the changes we are happening are not as a result of natural seasonal changes. So global LST anomaly trends show a clear long-term warming signal, and within most recent decades, generally experiencing more frequent and intense positive temperature anomalies than in earlier periods. So another application that I have performed are hotspots. So hotspots often occur in urban areas, dry regions and sparsely vegetated landscapes where surface properties and land cover can amplify the heating. So a hotspot analysis identifies locations that consistently experience unusually high surface temperatures, and this reveals areas that are most exposed to extreme heat. So this image on the left, we took our merged product at 1 degrees, and we categorized every single pixel for 2025 and assigned it a threshold temperature, as you can see at the bottom, from 25 degrees all the way up to 55. Now, if one single pixel over every day for the whole of 2025 was at that temperature for more than 2 days, we would then assign it. And then if that same pixel had risen, say to 40 or 50 or 55, that is when we would assign it that temperature. So as you can see, all of the areas in very dark red have pixels in the 2025 for more than 2 consecutive days at that temperature. And what we have found of trends over time, as we can see here, is that it allows us, we can see the rising trends in the number of pixels classified as hotspots increasing over time. So not only more pixels are being classified at hotter temperatures, that's actually happening more frequently. So this image on the right is showing over time, we have classified all of these hotspots from 2000 to 2025 for this data set. And you can see that the number of years with pixels classified over 50 and 55 degrees are increasing. And this is really important. So tracking hotspot patterns over time helps us to identify the emerging areas of concern, as you can see by the map, and including regions becoming more susceptible to heat stress, drought, and environmental change. So this analysis provides actionable information for urban planning, climate adaptation, and heat resilience, and supports targeted mitigation and resource management strategies. And hotspot analysis is key to understanding the amount of land and what regions across the world are consistently reaching higher thresholds of LSTs, such as over 50 and 55 degrees. And as I've explained, this is increasing. So this is really important work. So another application that I did here for the UK climate projections is to isolate trends. So great, we've got anomalies of trends over large regions. We can identify hotspots that LST are increasing in thresholds. What now? What does this mean, say, for an isolated region? So obviously I'm from the UK, so I'm going to give you an example here. So here are some plots I produced for the government under UKCP. And we can isolate these trends to the UK by taking these maximum LST values. So on the left, you have a UK per pixel maximum LST. So basically, over the whole of 2025, from January to December, every single pixel is classified, and we have made a map of the maximum LSTs. And then on the right, you can see a regional mean of those maximum LSTs. So based on different regions across the UK, I made the mean of them, and we can actually isolate what regions are consistently the warmest in 2025. And as you can see on the right picture near the bottom, the darkest red area is, of course, London. But it's no shock that the south and southwest are some of the warmest areas in the UK. That's well known. But we can also produce this seasonally, and it's interesting to see that actually some more of the north can be a lot warmer than the south in different seasons. So it's really important to isolate these trends. So by taking the maximum LST values and calculating these regional averages, we can keep isolating and help identify regions experiencing the strongest warming trends and changes in extreme heat events. And the spatial patterns in anomalies can also be linked to factors such as urbanization, land cover, topography, and regional climate differences, providing insight to the drivers of heat variability. So we look at these maps and we say, wow, there's a lot of high temperatures, especially in the south. Where now is the warmest in all of these regions? Great, in London. Why is that? That is directly linked to the urban heat island effect. And this is not just for the UK, this can be applied for any country and any region. So what do we do to continue to improve LST datasets? So global LST records have allowed us to monitor long-term surface temperature trends and variability and extremes. However, many important processes do happen at much finer scales than can be resolved by current climate data records. So our key knowledge gaps remain in understanding local heat exposure, urban heat island, agriculture stress, and thermal variability across heterogeneous landscapes. Advances in satellite observations, retrieval algorithms, and uncertainty characterizations are helping to address these gaps. And high-resolution LST datasets do provide a bridge between climate monitoring and actionable information for adaptation and resilience. So these developments just lay the groundwork for future missions such as the LSTM mission, which will deliver high resolution surface temperature observations at an unprecedented spatial scale. And that's what I will be going into depth more about this and improving our LST datasets. So to understand our LST datasets, we have some examples of key thermal infrared sensors we use to retrieve LST at different spatial and temporal scales. So we can showcase lots of great quality medium resolution data, but less in the high spatial resolution. So here we have MODIS, very classic, reliable data set, especially one that I have a lot of in-depth experience using. So this is what we could call a medium spatial resolution, 1 kilometer resolution, multi-channel of thermal infrared, and 2 instruments on 2 satellites. So you're probably quite familiar with Aquamodis and TerraModis, which are NASA satellites. And one is day and one is night and one is ascending and descending. So as I mentioned before, those maps we saw at the very beginning, we have SLSTR and AATSR, and they're also 1 kilometer multi-channel thermal infrared, and they are also highly calibrated. So we do have some high spatial resolution satellites as well. There's Landsat 8. This has 2 channels in the thermal infrared and a native 100-meter spatial resolution. And however, this only has a 16-day revisit temporally, whereas the SLSTR and the MODIS at medium, we can get daily, day and night, or ascending, descending retrievals. There's also high accuracies of under 2 Kelvin. We also have ASTER, and this has 5 channels in thermal infrared and a 90-meter spatial resolution, and that allows retrieval of both thermal infrared and emissivity. This is just 4 or 5 examples of sensors we use every day and sensors that we're producing LST CCI datasets for. So there are many, many more that are a lot coarser than this, especially in the microwave, and there are a lot more that are 1 kilometer and less. But we're quite interested in taking the data that we have. Great, we have that. How do we improve it? So we want to improve by downscaling, but why? This is because land surface temperature has a knowledge gap, the lack of extended temporal data with fine spatial resolution. So sometimes we come across with many data sets, not just LST. We either want high spatial resolution or we need it every day. And sometimes data sets don't have both. So this gap then limits our ability to accurately assess the trends and surface variations we're seeing. So without the long-term high resolution data, the development of targeted strategies for urban planning, climate adaptation and mitigation still is a challenge. And bridging this gap with comprehensive data sets is crucial for advancing our knowledge and creating data that provides actionable information for real-world decision-making. So this is a key target of the European Space Agency, especially in CCI and LST going forward. And I'm now going to continue and tell you how the progress that we've been making in our research team. So what have we done? So far, some very intelligent people in my group have created the optimal estimation, or used the optimal estimation algorithm to downscale LST. So they've created a new variation for LST. And this uses advanced techniques to combine temperature measurements with multiple satellites and produce more detailed and more accurate maps of LST. So this combines lower resolution temperature observations at 1 kilometre, as you can see in the top left plot. This is combined with higher resolution surface information at 100 metre, as you can see in the top right and the bottom left. And this is to improve the level of detail in the final product. And this is a very, very simplistic way of the way optimal estimation works. There will be papers published in the coming year, but we've done some significant amount of work on this. But in general, OE uses a gap filling sort of method to reduce missing data and improve coverage. So although areas filled in this way assume clear sky conditions and may not represent cloudy periods, but it's a step in the right direction, as you can see how pixelated the top left plot is as opposed to the bottom right plot. So this then also provides a propagated uncertainty estimates alongside the temperature data, giving users information about the confidence in each measurement. So all of our LST data sets always come with a propagated uncertainty measurement. And this is critical to understanding what the error is in our data, what the uncertainty, and how much confidence do we have, or what doubts do we have. And the majority of our data, actually all of our data, are at least within 3 Kelvin, but most meet the GCOS requirements, which are under 1 Kelvin of uncertainty. So we're pretty certain, we can say. So we have an example. Here's a case study, and this is Portsmouth in the UK. So we have a 1 kilometre scene here in Portsmouth, and you can identify regions, but it's not obvious due to the spatial scale. So we chose this area because there were a lot of cloud-free scenes available. And it also has coincident data for MODIS Terra, ASTER, and Landsat 8. And this allows us to intercompare and check the spatial outputs. So here is Portsmouth, here is Southampton, here is dense forest, and here is some agriculture. So this is the 1 kilometre over the area. So how do we do it? So we take the medium resolution 1 kilometre here, and we input, which is the SLSTR, and we use the high spatial resolution of 100 metre emissivity and NDVI information from Landsat or Sentinel-2. And we process this through the OE algorithm, and we can downscale this SLSTR to 100 metre with surface information. And this is what you can see here. So obviously we have much higher resolution, and you can pick out features a lot better than you could in the 1 kilometre, which was incredibly blurry. Now, 1 kilometre, not to say that these are not brilliant data sets, especially for climate analysis. 1 kilometre and 5 kilometre and higher are more than sufficient and provide a lot of information for regional climate trends, as the ones I showed you earlier. But when you're looking at urban areas and you're looking at high resolution data, this is the information we'd like to see. So this is what we have been developing. Here's another case study. We have Southampton. So here is an example where you can see the park in Southampton on the OpenStreetMap on the left in the circle. And in the 1 kilometre, you can't see it due to the centre of the urban area. But and you can see it's an urban area because it's a much higher temperature than the surrounding area, but you can't pick out the park itself. But in the downscale, you can see the cooler park here. So this is the same image downscaled to 100 meter, and now you can see that park, and that park is cooler than the temperature around the outside, and you could not retrieve that from the 1 kilometer. But this is an example of how high spatial resolution we can get more information. And this is because the 1 kilometer in the on the right image is absorbing too much of the surrounding, and the input emissivity for 1 kilometer would have just been classified as urban. Whereas when you look at the 100 meter, each pixel will have its own land cover classification and therefore temperature, which is why you can pick out the park. And this is just one example. So we're also looking at downscaling. On the right here is a new gap fill downscaling image that we're hoping to produce elsewhere. But this is thanks to the other work done by the incredible team and colleagues that I work with in the surface temperature group as part of multiple projects. So we now have a full UK downscale data set for 2018 to 2022. And this is great, but we now need to assess the performance of the data. So we use Landsat 8 data to do this. It is worth saying that the downscaled data, so if you take 1 kilometer up to 100 meters, is an estimation of the surface thermal properties. So you won't be able to use a downscaled product as a native representation. So for example, you won't be able to look at dynamic wildfires, for example, if a product like this is downscaled from 1 kilometer, because the emissivity and the surface properties are still from that 1 kilometer. But if a satellite is natively at a higher resolution, such as with mid-infrared sensors, then you'll be able to do that. However, it is great for climate trends, urbanization, and isolating surface temperatures and change. So this is a brilliant picture on the right, and this is also because in a 1 kilometer pixel, the dynamics are smoothed over. So dynamics below 1 kilometer can't be seen due to the lack of emissivity information. But yeah, so this is a brilliant image and just another example of the work we've been doing in our research group. So how does this link to LSTM? I'm sure a lot of people have heard about the Land Surface Temperature Mission. So the main mission and objective of LSTM is that it's an ESA mission developed by Airbus Defence and Space and set to join the Copernicus Sentinel system in 2028. And the University of Leicester are actually the science lead. We are the science lead for this, for the LST retrieval. And that is what the OE algorithm I've just showed you will be used in an LSTM. So the satellite will have 5 thermal infrared channels, a SWIR, so a shortwave infrared, visible and very near infrared observations, and this will cover overland and coastal regions in support of agricultural management services and even more, so all of the applications I was talking about previously. And it's currently undergoing an ESA prep phase to establish its feasibility, and LSTM improves upon Sentinel-3. So it currently will provide global LST measurements at a limited spatial resolution of 1 kilometer, which is Sentinel-3. And then this will be at 50 meters. So the complementary objectives to this as well is to support a range of additional services benefiting thermal infrared observations in particular. So soil composition, urban heat islands, coastal zone management, high temperature events, you name it. And this is where we will have native high resolution surface temperature, and this is where you will be able to get dynamic effects from. So continued, the primary objective here is to enable the monitoring of ET, in particular at European field scale by capturing the LST, allowing more robust estimates of field scale water productivity. The LST goal will be accuracy at 1 Kelvin, and the surface temperature and surface emissivity threshold will be an accuracy of 1.5 Kelvin and at 2% for the emissivity. So the evapotranspiration goal will be accuracy of 15%, precision of 5%, and field scale of 0.5. and the threshold for that would be about 20%. So we can see in some of the images on the right that the purpose of LST is not just for ET, but it can provide observations of high resolution LST, improve sustainable agriculture productivity at field scale, and predict droughts and address land degradation. And that's just some of the applications that this high resolution satellite will be able to show us. So this is a high priority Copernicus expansion mission developed by ESA. So the key, you can see on the table on the right, the general design concepts, but the key ones are that it will be a 50-meter spatial resolution. And that compares to the average of 1 kilometer. So that's a very big improvement on the spatial resolution, considering at the moment, some of our highest only 100 meters. It'll have a daily revisit capability, high temperature sensitivity, observations at peak daytime heating, ability to resolve field scale agriculture and urban heat patterns. And as I said before, we are our surface temperature groups are the science lead for this mission. So the overall key message, what do we want to take away from this? The higher resolution LST data allows us to observe temperature variability at scales where people, ecosystems, and infrastructure experience heat. Downscaling LST bridges the gap between climate scale observations and local scale decision making, providing more actionable information for users. Improved spatial detail helps also reveal urban heat islands, agricultural stress, and thermal hotspots that may be missed in coarser resolution datasets. Maintaining uncertainty information is crucial and is maintained all the way through the processing chain and to ensure confidence and traceability in the derived products. Combining observations from multiple satellite missions can also improve spatial detail and temporal coverage, maximizing the value of existing Earth observation data. We also have advances in LST retrieval and downscaling are helping to prepare the scientific community for the next generation missions, such as LSTM. And the future challenge is not only measuring surface temperature accurately, but delivering information at the right scale, resolution, and timeliness for the real world applications. So I hope you enjoyed, and if you are interested in connecting with us, you can see on the right there are 2 QR codes I hope will work, but I've also put screenshots if not for LinkedIn. And you can follow my personal journey on Instagram, my work account. And we're always open to collaborations, whether that's with industry or commercial, academic. And I'm quite responsive, so you're welcome to contact me or anyone in the team. Also, if you're really interested in LST, CCI and the work that the rest of the group, not just at Leicester, have done, you can go to the ESA LST CCI website, and a list of all of our publications and data sets can be found there too.
Thank you so much, Abigail, for this very complete and comprehensive overview of the LST-CCI project. We have a lot of questions. So you just mentioned in your conclusion that this LST project is really important for upcoming challenge related to climate change. And so my first question to you is, how directly do you think that LST data can be translated into public health risk metrics? For example, when we think about heat stress or heat-related mortality when there are very intense heat waves, given the fact that LST is measuring surface temperature and not the air that people actually breathe.
Yeah, so LST is extremely important for this, and it's actually one of the key reasons as to why we are increasing the use of our downscaling algorithms. And I think that it's hard to say because we've done so much work on the urban heat island, and I think the next advancement would be to link that data. So actually there's a PhD student and an urban heat island expert in my research team, and they have actually correlated crime data with heat stress and economic changes in cities and where it's more likely to cause sickness for the vulnerable during heat waves. And We have a lot of collaborations with the government and health agencies such as the UKHSA. This is something that we're definitely developing and really interested in. But because you can get such good information of the surface, to the difference of like between streets and car parks and buildings, you're then able to correlate information to do with people and human data, which then can make real impact. So another example is that we've been working with the UK police and looking at crime. We've also been looking at, we did some research, as you can find online, with Ordnance Survey, where we took an Ordnance Survey map and we overlaid a city land surface temperature heat map, and you could see what streets and buildings were more stressed than others. So it's definitely something that we're working on. It's definitely something that is really key, but we can't do that without the high resolution. This is why it's so important for not only the LSTM mission, but for the development and certainty of our downscaling algorithms.
Yes, and you mentioned that you developed a UK downscale dataset to support, notably, I imagine, heat health alert systems. Is there also the ambition to develop other datasets, also downscaled for other regions within
Yes. So the UK, we're based in the UK, so the UK is always our first case study because we know it, we understand it. As far as I'm aware, my colleagues who made it will be expanding to European cities and then hopefully the whole around the world. I would have to, and obviously I don't want to overpromise anything, but the plan is to expand it for sure. They've definitely said that. I think when the UK one gets published, it will be more clear. But obviously, if you'd like to contact me on these pages, I can inquire and give you like a direct example of where the UK dataset will be available and what will come. But obviously, that's project still ongoing and working with my colleagues, so they will definitely know better.
Right. Thank you so much. There are so many questions on how you downscale the dataset. So the first one being when you have cloud cover, for example, for the thermal infrared record, how do you handle the gaps, especially when you look at long-term anomalies trends?
Yeah. So we have cloud classification. Well, the data goes from level 0 all the way up to level 3, and I usually use my climate data on level 3. Level 3 means that it's on a grid, it's been gridded, and it's been corrected atmospherically and has had a cloud mask attribute to it. So all of our data sets have cloud masks, and unfortunately it's something that's native to thermal infrared, and that's what we call the clear sky bias. It's only, we're only really measuring under a clear sky. However, when you aggregate these pixels over time, they smooth out. So when, for example, when you were looking at the maps that were at 1 kilometer and anomalies over time, you're not just looking at pixels per day, you're averaging them over months and years. And this is enough for a climate signal. Obviously, we do a lot of corrections to our climatological trends to make sure that it accounts for missing days, missing years, and to make sure that it is correct. So on a climate scale from like 1 kilometer up, due to the nature of testing anomalies and trends, it gets smoothed out. With the higher resolution data, obviously you are limited, especially to like cities such as my case studies in Portsmouth and Southampton. You are limited to the amount of clear sky days, and unfortunately that is just a natural inherent problem of thermal infrared. We can't change that, but what we do is we make sure that we gather enough data so that we can be sure, and that's also why we propagate uncertainty, so we know that every pixel we do have a temperature for, how certain we are, so then we can trust the output. And most of urban studies, there are studies of climate trends in urban, but urban is more on a daily to monthly scale in terms of looking at spatial distribution as opposed to trends. Climate science is looking at aggregated trends. So you can it's obviously a problem that we have missing data, but as long as we know that the data we do have, we are certain about and have confidence in, then we make sure that's very clear to the end user.
There's another very technical question on the downscaling process. Someone is asking, couldn't we leverage XGBoost for downscaling with error partitioning to transition to microclimate resolution even finer than 1 kilometer using machine learning?
So this is a great question, and my PhD actually used machine learning. I use CNNs, but I've not used XGBoost. There's two things here. So OE, so optimal estimation, is extremely accurate for us. So and we can track everything. So OE produces Jacobians, and we are able to propagate the uncertainties through the entire algorithm through the downscaling. There's no guarantee that in the machine learning you can. I'm not saying that you can't get uncertainties from machine learning, but it is a lot less developed than a statistical model. Also, there are so many unknowns in LST. You need to be able to parameterize for every single one. So it's all right saying, great, a machine learning model can downscale, and it can, because my PhD, I was able to downscale coarse resolution microwave to 5 kilometers, and make a merge product. And that's great for climate, but for urban, that's not. You need all the information. You need to make sure that the machine learning isn't guessing. And because you're not just downscaling based on another resolution, you're using extra information. And the optimal estimation algorithm has performed the best. And there is a paper which you can see online. It's a round robin. And they basically tested and had an analysis of every algorithm they could think of, and OE outperformed all of them by far. So, and it gives the scientists enough control over what's happening to the data, see what's happening to the data, so that we can also propagate those uncertainties, and we care about those uncertainties. And if the data looks good and we don't have an uncertainty, then there's no point really using it for in LST context. That doesn't count for all ECVs. And the whole point is to produce an accurate uncertainty. So, and I'm not saying that there isn't sort of like, a perspective for machine learning, but at the moment, OE does outperform, and we can control everything that's the algorithm's been done, and it's very effective.
And on the applications of these downscale products for environmental questions, do you think it's ready to be integrated with, for example, flood susceptibility or drought monitoring, for example, in areas where you don't have enough in situ temperature datasets?
Yeah, definitely. There's something that I've actually been personally working on. I also work on policy and impact, and I'm working on drafting a policy briefing paper, which I actually have just drafted, and looking to publish and try and push for a heat wave dashboard or a heat dashboard for LST. So as I mentioned before, and as most people are aware, when you think of temperature, you think of air temperature or T2M, as those who use it understand. T2M is great, but it's interpolated between stations. You're correct. LST does produce, data, as long as it's a clear sky for every pixel on Earth. This needs to be utilized. It is underutilized, and a lot of the data sets, as long as you have the correct resolution, are ready to be cross-correlated with many applications. I think it's just getting the understanding and the knowledge out there that LST is an option. LST has grown so much. Like, for example, when I started my PhD 4 years ago, and now I've been a postdoc for a year, so it's 5 years ago, there were about 4 or 5 people in the team. There's now like almost 13. And that's just our research group, because it is an ECV and it is a priority. But many people just think, air temperature, not land surface temperature. And they're both complementary, but we are trying to push not only the use of data sets. So if anybody wants to use or is inquiring about using LST as complementary data set, feel free to reach out. We're always there for whether it's advice or collaboration or anything along those lines. We can see what is possible, but it's LST is there to be used, and it should definitely be utilized more.
Yes, as you said, LST has grown a lot, and in fact,
Yeah.
there's many more commercial enterprises to look at LST data. For example, Constel IR, SatView. And the question that I'm reading now is, how do you foresee the products and applications evolving in the public domain based on the combination of the public reference mission that you mentioned, for example, LSTM and S3NG, with the high resolution thermal commercial missions?
So, the thermal commercial, I actually, ironically, have been talking to a lot of these companies really recently as part of my policy and impact work. And the majority of findings that I have found from commercial is that they're very niche and they're very early days. Some of them are very mature and they have incredible data sets. Very, very few of them have propagated error and uncertainty. And that is the key. We stand by the fact that our data sets have uncertainties propagated. You can see a true propagated uncertainty for every variable, and that's including random, systematic, surface, the total uncertainty. And there's in our eyes, using data you can have confidence in and that is producing an accurate output is worth that. And I understand that a lot of companies have produced really high data resolution. Some of them, as we've seen, I've spoken to a company recently, some of them haven't even started looking at land masking. So they've not even calibrated or got an algorithm for the ocean to separate ocean from land. Some don't have uncertainties. Actually, most don't have uncertainties or errors. And I'm not saying they're not useful. They are definitely useful because there's so many applications such as, mid-infrared wildfires and thermal stress of individual buildings that LST doesn't have the capability to do. However, LST and the process in which we're using the downscaling or even just the production of the climate data records at all scales of LST here as part of ESA-CCI, it's imperative that there are propagated errors and uncertainties, and that is the only way you can have confidence in the data. So I would imagine that the commercial side I would like to hope, develop uncertainties and errors, but a lot of them use machine learning, and a lot of them are downscales of downscales. So they'll take an already downscaled data set and then downscale it more using machine learning, and the errors will be through the roof. So I think it's a playoff between what you need, what you can get, and what level of uncertainty or certainty do you want in the confidence, and why are you using it? So all of our data is open access and all available online, freely downloadable. And like we said, you can always contact us if you have any further questions about that.
Yes, it's great that you're mentioning that. And on that note, could you also share the paper that you mentioned on comparing downscaling algorithms to OE?
Yes, it's the round robin one. I don't know if I have it right here. Let me just quickly check. Let me see if I can find it. I can ask my colleague because I believe he read it. He wrote it.
We can always send it to the participants after the
Yeah,
webinar ends
yeah.
and put it.
I'll get it. I'll get the
website.
round robin, and I will make sure that it is sent through to you guys so you can forward it or link it with the rest of the recording.
Yes, which brings me to the many questions asking if this is recorded and can we see it after. Yes, the presentation will be shared and we will put it on the climate.esa.int website where you can see all the past webinars. And this will also include the paper that you mentioned right now. And just one final question. I'm trying to see if I didn't miss anything. Somebody is asking, how do you downscale in wintertime when there is negative values of NDVI? I'm asking especially about Arctic regions.
Yeah, so Arctic regions, these are good questions actually, because my master's is in the Arctic and I've just I've done a lot of work in the Arctic actually, in Svalbard and Greenland, and Arctic Sweden and Finland. And the issue with that is that on the climate side, when I use it, you either get nil LST value, or you can most of our data sets will have a count of number of cloudy pixels and number of clear sky pixels, and you'll be able to use that as a weight. In terms of the downscaling, it is fully dependent. To downscale a coarser or medium resolution to a high resolution, you obviously need the data. If you don't have enough, all pixels will be downscaled, but if you don't have enough, then that will be factored into the error uncertainty. On the climate side, there's something called this sampling uncertainty. So when you propagate uncertainties at the climate level, say the 1 kilometer and above, you can basically weight in a factor of, okay, we have a higher uncertainty because there's only, say, 3 pixels in this scene, or you have a lower uncertainty because you have loads of pixels in that scene. Something very similar will occur in the downscaling. I don't work on the algorithm, so if you would like to contact us, I can get like an exact response for the downscaling in the urban from Mike Perry and Charlotte Payton and Ben Courtier and Darren Gent, who are the key OE people in my research team. But my educated guess would be that it would be factored into the error and uncertainty propagation.
Thank you so much, Abigail, for this very comprehensive discussion and all your responses. As you said, you're really responsive. If there are additional questions, feel free to reach out to her and follow her research group. Again, this is recorded and it will be posted on the Climate ESA website. One final word from my end. As I said in the beginning, this is a recurring webinar series. So the next one will be in July, focusing on the fire CCI dataset. It will appear shortly, right? It's on the 22nd of July at 4 p.m. CST. And it's a good follow-up on the discussion that we just had on LST dataset, as we will be diving into the Fire CCI project. And this will be introduced by Emilio Chuvieco, who is ESA Fire CCI scientific lead based at the University of Alcalá in Spain. So we invite you to follow the website to sign up for this upcoming webinar. And thank you so much for all your questions. And again, many thanks, Abigail, for this great presentation.
Thanks so much for having me.